start almost on time so that the latecomers know that they are late. Let us sort of remember what we did so far. So what we looked at was we did take a domain D. We had two boundary points that we called X and A. I think that was what we started with. And what we looked at was a discrete sort of, we took a delta small, and for a small delta we used the lattice approximation of this domain on mesh size delta. And we decided to color the boundaries of this lattice approximation in two colors. And so for each lattice approximation, we could define the random interface running from X to X delta to A delta in that domain. Which basically goes around the green cluster attached to this part. So it can look like this. And what we said, the first thing we said was that when you let delta go to 0, here the set of probability measures on random curves that this defines is tight. Therefore, there are subsequential limits when delta goes to 0 for the law of this random curve, when you let the mesh of the lattice go to 0. Then what we said was, okay, assume gamma is a subsequential limit. So assume gamma is if gamma is if the law of gamma of the random curve gamma is a subsequential limit of the law, or let's just say a limit, because is the limit of the law of gamma delta n for some delta n going to 0, right? So that's what we started. We said, assume gamma is one of these limits. What can we say about it? So what we said was that then, that's what we concluded with last time, if then for each B and C, so the reason I explained it like this was just to stress the fact that in the definition of gamma, you don't need to know where B and C are, right? So the definition of gamma delta, and gamma is just depends on X, A, and the domain. And so for each other 2 points, B and C, if one defines for any t, so what do we define? So we have 0, gamma up to time t. Well, no, that's a 0x, gamma up to time t. Here's A, that's where we're going at. Here is C, here's B. So we defined the unique conformal map on the equilateral triangle of this slit domain, such that A goes to A, B goes to B, C goes to C, and xt goes to here, right? So the picture I did draw here is just a definition of xt, where we will just identify xt with I don't know, I probably used this one with this length. So if this is length is 1, this length is xt. Then xt is a martingale. Okay. So it's a martingale with respect to the filtration generated by gamma, right? because we said that the probability, or that xt is the probability of a certain event. That's what we said, gamma hits AC. How does it work? It's AB before BC given gamma up to time t. So that's what we proved last time. So there's a little remark that you can make immediately, which is that if you look at this definition of xt as a definition itself, it's quite clear that xt will be continuous with respect to t. I mean, that almost surely it is a continuous function of t. Well, basically, just because this is a Loewner chain, so this is growing locally and continuously, right? So the image, you know, of the tip under this conformal map when this domain shrinks a little bit will be continuous, so that xt here will not jump, you know, from one point to the other in this picture. So that's a simple exercise to check. So it's quite clear, you know, that if at some point tx would jump from here to here, then that would mean that somehow gamma would have to jump from one point to another in the domain, and that's not allowed. So we know from the construction, from the definition, of xt, we also know that it is a continuous function. Now, I want to make a little comment. So, you see that in a way, knowing where xt is telling you also is another way to describe the driving function. Remember that when we had this Loewner chain, so we said we start with in the upper half plane, right? And we said that for each sort of gamma up to time t, we define gt to be the conformal map normalized at infinity, which is telling you basically you take the infinity goes to infinity, so you map this here onto the upper half plane. Infinity goes to infinity, the derivative at infinity is 1, and the second derivative in some way is 1. So you just say that gt of z is defined by z plus little o of 1 as z goes to infinity. Right? And then you define wt to be the image under this map of gamma t. Okay? And what I explained during the sort of Loewner chain description, and what Christophe explained also, was that if you know this function wt, then you can recover the entire curve, right? The idea being, roughly speaking, that you know you are something that is growing, you know, like a piece of grass or whatever, and then it grows locally at w, and you move w, and then in some way this creates a two-dimensional thing in the plane. Now here, what we have here in some way would be to say, well, I have A, B, and C here, and X, I have a curve here that is growing here. Now we can say, well, I'm going to use, instead of, it's natural here in this picture to still, instead of using the conformal map normalized infinity, to use the normalization that maps B onto B, C onto C, and A onto A. And then this define xt as being the image, so if this would be, say, GT, the map as GT of gamma t. Right? So the situation here is similar in the sense that it should not surprise you what I'm going to say you in a moment, which is that if I know xt, if I know this function xt, in some way I will recover the entire curve gamma also. Because it's just, you know, a different way to, it's just a matter of normalization to decide which is the conformal map we're looking at. And it's quite clear that if you see here, so for instance, if you look at, if you know xt here, the function xt, so it's not entirely obvious how to get back to here. It's not entirely obvious. I mean, here it's obvious how to get back from here to here by mapping a to infinity and then choose the right normalization. But you see that if you just forget about this picture here, again, you have some piece of grass which is growing. You move the xt, and then you just well, the grass growing is not very good because it doesn't grow at the tip; it grows at the root. But you just move, slightly, how the direction of where you grow, and using xt, and that's enough to understand that picture. So in the first picture here, what we had was that. Imagine that here we have our 3 points. Let's call this one B prime, this one C prime, and A prime to be infinity. So why do I define these 3 points like this with primes? It's just because here the names A, B, C, and X are already taken here in the domain D. So what you should think of is that you choose one fixed conformal map from D onto the upper half plane. Right? This one is fixed, and for this conformal map you take A to be infinity and the image of X to be this guy X prime. And by definition, the law of this curve gamma, right, will correspond to a growing set of Loewner evolution. Of a Loewner evolution on the right-hand side, because these two domains are conformally equivalent. Okay, so imagine that we have something in the upper half plane with these 3 boundary points here. So what we know are is the equation that for each z in the upper half plane, we have something like that. Right? That's the equation of Loewner's equation when this thing here is parameterized by half-plane capacity. That's what you get. Okay, the relation that tells you that if you know the function Wt, then you know the conformal maps Gt by solving this ordinary differential equation with G0 of Z being Z. Now, the first remark that you want to make now immediately is for each Z that is away from the tip, right, the evolution in time of GT of Z is smooth. It's a C1 function. Okay? It doesn't wiggle back and forth. When you choose this normalization at infinity, in some way you smooth out this wiggling of gamma, and the evolution with respect to T of GT of Z is smooth. Okay, that's the first remark you want to make. So in particular, what you see is that let's take it A prime is just 2 over GT so B prime. That you have these 2 things. Okay. So how now we want to make to see what xt is somehow, what this conformal map here, what this value xt corresponds to in that picture. So what we're going to use is the unique, so let me erase this little piece here. So here, right, so here I have gt of v prime, gt of c prime, and I'm in the upper half plane. Here it's the guy which is that is way. Okay. And a, you know, gt of a prime is still infinity. And I messed things up with my signs. Maybe I should put c on the left-hand side here, but okay, let me put c prime here on the left. Just for you to have the picture in the right order. Now, what we're going to use is the conformal map. So we defined psi which is the conformal map from the half plane into the equilateral triangle, right? In such a way that basically if you take the image of the 3.01 and infinity, that they correspond basically to infinity, 1, and 0 here. That's a uniquely well-defined Riemann map, and it's actually easy to characterize this conformal map. This is what you learn in complex analysis textbooks. This is a Schwarz-Christoffel map, and it's easy to see that it satisfies a certain ordinary differential equation, and something like say, for instance, what you get is that for any x between 0 and 1 in that picture, I think the equation is psi of x is constant times the integral between 0 and x of dy over y to the 2/3, 1 minus y to the 2/3. So, or in other words, that it satisfies something of this equation. That's, you know, standard theory of conformal maps that tell you this. You know, Schwarz-Christoffel maps are simple because, you know, on the boundary, things are just straight, except that, you know, some corners. And so what you see happening here are the things involving the end corresponding to the angles at the corners and nothing else. And the value of the corners, which correspond to y equals 0 and y equals 1 here in the picture. So, okay. So we define this conformal map here. And so it's very natural here to map this picture here onto the picture like this, right? By mapping these 3 points onto these 3 points. That's a natural thing you want to do. So remember, in our definition of our martingale, that's what xt means, right? What we did is xt was the image of the tip, right, of the domain, I mean, of the image of the tip here by the conformal map that maps the remaining domain here on the triangle in such a way that ABC are mapped onto ABC. So what we have here is we have the conformal map here up to time t, right? And this is mapped here onto the upper half plane. Then the upper half plane is mapped onto, slit upper half plane is mapped onto the upper half plane. Again, so if we want the conformal map from here to here, we just need to compose finally by the conformal map, which is just psi of minus gt of c prime divided by gt of v prime minus gt of c prime. Right? First, you know, renormalize things in such a way to map this to 0, this to 1, and this to infinity. That's just this map. You know, you subtract first gt minus, you subtract, so is it a c? Yeah, that's a c. You subtract gt of c prime to make this one to 0, and then you multiply by the real number so that this one goes to 1. You're still, and then you use your conformal map psi, and here you are. So the conclusion is what? Is that xt is a function of all this mess, and this function is just psi of, okay, let me write it. You know, what I'm doing now, just for you to understand what, I want to justify the fact that xt is just defining, characterizing the entire function, gamma. Right? So here we know that xt is equal to psi of w minus gt of, I'll use the c, and psi is a very smooth function. Okay. So here you can just say, you know, w now, consequence of this is that w t is gt of c prime plus psi minus 1 of, well, xt times gt of p prime minus gt of c prime. Okay. So if you look carefully at this, and this, I mean, this together with this, right? You could just replace wt by its value here, given here, right? Suppose you know only xt, right? The only knowledge you have is xt. You have this formula, so you replace wt by its value here. What you get here, the derivative with respect to t of gt of b prime is going to be some function, which is a fairly nice function. I mean, there's xt there, and then there are things that involve gt of c prime and gt of b prime. That's all. Right? And the way gt of b prime and gt of c primes are, you know, involved is smooth and nice. And same for here. Right? So once I give you xt, you have a nice, simple, ordinary differential equation for the pair gt of b prime, gt of c prime. You know, gt of b prime. So if one knows if xt is given, this two-dimensional thing solves the simple ODE, so it's well defined. Up to the time maybe where, of course, they hit WT. Okay. So now, what I explained to you is if I know xt, I know gt of v prime, I know gt of c prime, all these functions. Well, so I know wt also. Okay. So wt is also determined, okay, up to the time at which the curve maybe hits b prime or c prime. So if wt is determined, that means that you know gamma. So this was a very slow justification of the fact that if you know the function t gives xt, you know the entire curve gamma. And actually, we know even more. Because if you look carefully at what you get here, you remember psi is this analytic function, which is fixed. You know, so psi minus 1 is also a very nice analytic function. So I said with respect to t, these are, you know, these are C1 functions. Okay. So this tells you that the relation between, I mean, that in some way WT is a smooth Okay, there's psi minus 1 of x over the place here. But apart from that, you know, it's just a smooth transformation of psi minus 1 of xt. So wt is some smooth function of xt. Okay. So maybe there's always one problem with these type of topics when one touches, you know, several parts of mathematics where, you know, each of us usually has been trained as a better training in one part, you know. So for some people, you know, stochastic calculus is the thing they learned, you know, at first graduate course, so they are very familiar with what the notion of semi-martingales and Ito's formula and so on, and that's something, you know, as soon as you can play with this in this playground, you're safe and you don't give any simple justification. Or you started with complex variables, and then this you know, once you end up here, you are very nice and very safe and so on. And then maybe the stochastic analysis part is not so clear. If you are starting with particle systems, then the percolation FKG stories is nice, but the rest maybe you are not entirely confident about. So here, at least for me, you know, now you enter, you know, in safe playgrounds, because I was, you know, brought up in Paris 6, where people, you know, teach or find properties of Brownian motion before mentioning, you know, that particle systems and Ising models and these things even exist. So, well, at least it was very good for me, and I liked it, so I chose to do it like this. So. But so here we have. So there's one remark I want to make now. So which is, I said here, xt is a martingale with respect to the filtration generated by gamma. So if you condition A on the information given by gamma, then you know xt. But what I just explained to you is that the information given by xt itself is the same as the information given by gamma. Because if I know x up to time t, I know I can recover the function gamma, and on the other way around, if you know the function, if you know gamma up to time t, you can see what xt is. So xt is a martingale with respect to its own filtration. So, you know, it's just looking at the evolution of xt itself gives you a martingale. It's continuous. So that's a very classical result, that if you have a continuous martingale, xt, then necessarily it is basically a time change Brownian motion. It follows, roughly speaking, what a continuous martingale is that you are given a Brownian motion and what x is doing is it's following, you know, the trajectory of this Brownian motion. It's following this guy continuously, you know, always to the right. But, you know, the speed at which it goes can vary. You know, and, you know, it may speed up, it may stop at some point, it may do, you know, some, and it may decide to speed up or not, etc., just by depending on what it sees, you know. Maybe they say the martingale will decide, you know, first time I hit 1, I start going twice faster. That's okay. This will still be a martingale. Okay. Now, if I see the trajectory with respect to time of a continuous martingale, so, you know, maybe from time to time you slow down, from time to time you speed up. There's a simple way to recover, you know, the speed at which you discovered, you know, there's a simple way by seeing this thing, to put it back to the Brownian motion. So roughly speaking, you know, like, okay, I've been to Buenos Aires this weekend, so if you imagine that you have a regular bandoneon with a regular, you know, it's nicely put in the box with regular oscillations of your little, how you say, what I'm saying is just, roughly speaking, that's a regular bandoneon with or you might say just a simple random walk, which is simple and nice, regular with respect to time. And then at some point, you see something which is right? Well, by looking at the picture, you know what to do, to go from here to here to put it back in the box, right? You just have to, make it such a way that each time you go up by one, or each time you go down by one, you have to rescale in a certain way that takes the right size here. This linear by part transformation from here. So here in the Brownian motion, of course, it's not exactly the same because you don't see this, but what you see is the quadratic variation, which is roughly the speed of oscillation of the Brownian motion on infinitesimal level, which basically tells you by how much you had to rescale the simple random walk. So here, by looking at the little piece of the Brownian motion, you know basically on each little small piece how much you went up and down, roughly speaking. Okay, it has an infinite length, but you can see it. And so here, going up and down, this is something you see also here. Okay, so it's so by just looking at this thing up to time t here, there's a quantity which basically tells you how much you went up and down, which is called the quadratic variation of so if this is x, or a martingale, say m, so what this quantity is basically the time in the corresponding Brownian motion that has been going on, that tells you how much you've been going up and down here. So what the Dubin-Schwarz says, martingale is a Brownian motion running at the speed given by this quadratic variation. So all I'm saying is that behind the scene of this continuous martingale xt, you have two pieces of information, which is just that there's a Brownian motion behind the scene, and they are traveling along the path of this Brownian motion at a certain speed. So that's the first. So I'm sorry, maybe I shouldn't say these elementary things. Okay. Now, the other thing that we know is that if you have a Brownian motion, so if Bt is a Brownian motion, you have Ito's formula. And Ito's formula tells you that if you have a C2 function of Bt, then this is just f of B0 plus something that is written like this, plus 1/2 of integral between 0 and t and f double prime of Bs ds. Right? So where does this come from? Well, this just comes from, you just decompose f of Bt minus f of B0 into, infinitesimal, increments. Okay, I think Christophe has said these things. Okay? And now you just do a f, f is a C2 function, you just do a Taylor expansion of each of these terms. And in the Taylor expansion, what you will see will be just each time you have f prime of bj over n times the increment. Right? And then 1/2 of the second derivative times the squared. And then you have some little o of the square. Now, when you sum these things, if you look at this guy, the sum of this guy, it's basically the sum of what somebody who is playing along the Brownian motion will collect. So, you know, the Brownian motion tells you if you win what at the increments, say, between gt over n and j plus 1 over n times t would be basically what, so I don't know, the stock markets are doing between gt over n and gt plus 1 over n, whether it goes up and down, and that's just a martingale. So each time you have the information at j over n, jt over n, what will happen between jt over n and the next time, you know, will be just, again, a mean zero thing, independently of what has happened before. So basically, this sum is what somebody will collect, you know, at the end by deciding each time, at each time jt over n will decide, okay, now that's the amount of money I put on the table, which is f prime, right? And so then I win or I lose, depending by, multiply this by the factor given you by the increase or decrease of the martingale. So it's quite clear that this guy, when n goes to infinity, will roughly speaking converge to a martingale, because, you know, each time you play and then you win or lose at between all the times, and roughly that's what the person, you know, this quantity, that's how it is defined. That's the limit of these guys when n go to infinity. That's what the person, you know, that, you know, plays along the Brownian motion, but it plays, you know, at each time t, it will put that money on the table and collect what the Brownian motion collects on. And the important thing is that this guy is still a martingale, right? Because here, whatever you do, you cannot, you know, make win more, lose, or be sure to win or to lose. It's always a zero mean thing. Now this thing, this quantity here, this is very small. You know, the Brownian motion has the square root of t scaling, so between an interval of order 1 over n, it will be roughly a distance square root, 1 over square root of n. So when you take this square, roughly speaking, this guy will be a random variable that has mean 1 over n, or here t over n, okay? And it cannot be very large because the Brownian motion has a fast decaying tail. So when you sum all these things, you have some law of large number that just tells you that the sum of these guys will just converge to this. Okay. It's law of large number says it's as the same as you would here, just, you know, so this is a random quantity, but each time you get you collect something like of order 1 over n. So when you and the next term are smaller order than these ones, so they're smaller than 1 over n, so they disappear in the limit. Okay, that's Ito's formula. Now, Ito's formula works also for a martingale M, right? And it's exactly the same story. What you will end up is f of mt. And for a continuous martingale, you'll get, this is just f of m0, plus integral between 0 and t of f prime of ms dms, plus 1/2 integral between 0 and t f double prime of ms. And here you have this guy. Why? Because if you think about it, this guy is just a time change of this guy. Now, the way this thing was defined, this dbs, f prime of s dbs, right? You know, the time parameterization of along the path did not play any role, right? It's just the guy that plays simultaneously with m, and if m wins, it gets what m wins. If m loses, it gets what m loses. But so roughly, the definition of this guy is basically just the same one as what you get here. But here, what you have is this quadratic variation that tells you that because the ds, the time that passes for the Brownian motion, correspond to this is the d of the quadratic variation of m. Right? So this is just, you know, time change version of this guy by the time change given by the quadratic variation. Okay. Now, there's a remark that you can make immediately, which is that if I have a continuous martingale, so I'm just, you know, trying to explain to you that, you know, Ito's calculus, you know, for general what we call semi-martingale, is something very natural. It's just the same as Brownian motion, except that you have the time change and that you play a little bit with it. You see that this quantity f of mt, right, it has two parts. Here, this guy is constant. Okay, so we don't care. This guy, I just said, is a martingale itself. Actually, it's what we call a local martingale, because maybe something blows up. And now, this guy is a smooth function, in some way, because it's a function which has a finite total variation, because when you look at dm of s, you know, it's just the derivative or differential of a, not the differential, but the formal, say, differential of a continuous increasing function, and the value at 0 is 0, and the value at time t is just this quadratic variation at time t. So this is a, you know, smoothly varying, not smoothly varying function, but it's a function which has a finite total variation. And because you have a function which has a finite total variation, you know this is not a martingale. You know this. There cannot be any martingale in there, no martingale part, because a martingale part would be a time chain Brownian motion, and this one, you know, would have to, cannot have a finite total variation. So here what you see is that if I take a, you know, a martingale, I take a C2 function of a martingale, what I'd end up with is something which has the form a martingale, continuous martingale, plus a function with, finite quadratic variation. And therefore, what you end up with is, now if I take G, you know, if I take a function which is C1, or let me write it like this. If I take a C1 function here of some function which itself is the sum of a continuous martingale and a function with finite, bounded total variation, then by doing the same, you know, Taylor expansion, you will get these terms. You know, that they come from the variation of m collected along the way. And then you have a Taylor expansion coming from the variation of v collected along the way. But because you know that v will have a finite total variation, the only term, you know, that will come from the variation of v, or from the mixed term between v and m, when you expand the Taylor expansion of what happens to this sum between tj over n and tj plus 1 over n, will just be this. Okay, so this will be just the same as this. So let's write this. This one would be, say, yt. Then you get just f of yt y0 plus integral between 0 and t of f prime of ys dms. Plus integral between 0 and t of f prime of ys dvs. That's what comes from the increments of v in the Taylor expansion. And then plus 1/2 integral between 0 and t f double prime of ys dms. That's what comes from this second order term. And all other terms, you know, disappear when you let the mesh of the lattice go to 0 in the end. Okay? So it's just the same story as before. So in particular here, what you see here is that if I start with a smooth function of something which is a sum of a martingale and a process of infinite variation, then I get here a martingale, and then the part which is not a martingale is the sum of the integral of the first order term with respect to this and this guy here. So in particular, what you get is that if I take something which is a sum of a martingale and the process with finite variation, and I take a smooth function of this guy, what do I end with? Again, with some process of the same type, which is a sum of a martingale and something with finite total variation. Right? So these guys, so the class of guys which is a sum of a martingale or something with total finite variation, is what we call semi-martingales. And they are stable, you know, on the C2 transformations. sorry, it's just a sort of... Now, let's come back to what we have here. We know that xt is a continuous martingale. So what we end up is a psi minus 1 of xt, which is a very smooth function, analytic function of xt. So that's a semi-martingale. You know, you just apply Ito's formula. That's just this part here. So psi minus 1 of xt is a semi-martingale. It's the sum of a martingale, continuous martingale, and a process with finite bounded variation. Now, I know that this guy here is a C1 function of t, and this one is a C1 function of t also. Right? So from that, I conclude immediately that Wt itself is the sum of a martingale and a process with bounded variation. So, which means Wt is in this class of semi-martingales, always with respect to the filtration generated by the curve gamma or by x or by w, they're all the same. Okay. So Wt is a semi-martingale. So what do we know about Wt? So Wt, remember, our goal is to say that Wt has to be a Brownian motion running at speed 6. That's you know, our ultimate goal, to say that, identify the limit as an SLE. So we know that Wt is a semi-martingale. And we know that xt, now we go the other way around, which is psi of Wt minus gt of C prime divided by gt of B prime minus gt of C prime. We know that this is a martingale. Okay. And here, everything is more or less explicit because we know the derivative with respect to time of this one, this one, this one. Okay, Wt we don't know, we want to understand what it is. And psi we know exactly what this function is. Okay. So let us define just for convenience bt to be gt of b prime, ct to be gt of C prime, and decide that Wt is mt plus Vt, where this is a martingale, continuous martingale, and this is a finite variation guy. I mean, finite variation process. Continuous process with finite variation. So now, we know that Wt minus gt of C prime divided by gt of B prime minus gt of C prime is, again, itself a semi-martingale. And so we just apply now, we are going to apply this type of consideration to the computation that leads to dxt. Right? In other words, we're going to write xt is x of 0 plus, there's a martingale term, plus bounded process, I mean the integral of the process with bounded variation plus the quadratic term here. And we know that the process we get in the end is a continuous martingale. That means that in this expansion that we will compute here, you know, the part with bounded variation has to be 0. So we do this. What we know is that dbt in that picture, right, is 2 over bt minus wt. That's the definition of the Loewner equation. dct is 2 over ct minus wt. So let us first understand what happens to WT minus CT. Let me immediately write this like this. D of xt. Maybe I will maybe be too fast, but you'll see in a moment what I mean by this. This psi prime of xt times dmt over bt minus ct plus psi prime of xt dvt over ct plus put it minus psi prime of xt times d of 1 over bc minus ct plus 1/2 psi double prime of xt. And the quadratic variation that you collect, you know, by in this way will be just 1 over this. So what I mean by that is just, you know, this is just a differential version of, formal version of this equation, this type of expansion here. I would say dyt is just, you know, f prime of ys dms plus f prime of ys dvs plus this. So you just look, you know, on infinitesimal level what happens between two successive times t over n and tj over n and tj plus 1 over n, and these are all the terms that come out. Because you do the Taylor expansion of this function between basically jt over n and j plus 1 t over n, and so you differentiate with respect to different possible, you know, different possible things that fluctuate, and all other terms, you know, are smaller order. They disappear when you look at the interval. Okay, so what we know is that this has to, I mean, we know xt is a martingale. So what we end up with here is just that psi prime of xt dvt over bt minus ct plus, now what you end up here, okay, d of 1 over bt minus ct, this is something you know because you know what dbt is and what dct is. Right? You mean I missed... you mean CT? Yes, this, you mean? No, I think that's... I differentiate this part, right? So this is in front. Yeah, you're right. I'm sorry? Right, so I forgot this one also, you say? Minus, okay. Plus psi prime of xt, well, there's a minus again, dct over bt minus ct. Thanks. So let us try to recollect, right? This guy has changed, right? So this is accounted for in that picture here. So maybe there's no minus sign anymore because I did put the minus thinking of I take 1 over a thing. But okay, so that has been accounted for in the second line. This one moves, and it's accounted for in that line. Yes. Now, this one moves, and this will give a first order contribution, first order term. So that's the first order term coming from the variation of this guy. And the second order term coming from the variation of this guy here. Okay, so what you end up here with when you so you see that everything is completely explicit. Okay, in the sense that
why you have the derivatives, the xt derivative
where is the
sine prime of xt, why xt derivative?
Oh, sorry. So it's not xt. You're right. It's apologize. Okay, so what you end up with here is basically, so what we want, so conclusion is that something has to be 0, because this is a martingale. So what has to be 0 is that of course, this guy is a martingale already, so it's just the sum of the rest that has to be 0. So that means that psi prime of x tilde t, over bt minus ct times dvt, plus these 3 lines have to be 0. So in other words, maybe I can just say this I remove, and so 0 has to be equal to this. Okay, so since I already started to mess up things, maybe I don't want to make things worse by messing up the computation, but what you end up with just by, you replace the value of bt minus d over 1 over bt minus ct by what it is, and dct by what it is, you reduce everything to the same denominator, and the equation that I just wrote can be written as dvt over something like bt minus ct c prime of x tilde t plus, now here I'm going to use something also that over 2 times bt minus ct squared times dmt minus 6 times dt. That's what you end up with. So why do you end up with this? So what did I use here in this computation? Well, I just used the expression of d of bt, d of ct, d of ct here. And something about psi. And something about psi that you use is that there's a, remember there was a differential equation for psi. Particularly, I said that psi, psi prime times something was equal to psi double, psi prime times something plus psi double prime times something else was equal to 0. Right? So you just use this. So that means that each time you see a psi prime here, this psi prime here, and this psi prime here, and this psi prime here, not this one I kept, but basically this psi prime here and this psi prime here, you replace by the corresponding thing in terms of psi double prime. So what you see is nice, which is that all these terms, they have the same factor in front, which is just this one. And there's this guy that just comes from here. Actually, you recognize it, right? It's 1/2 psi double prime dm over b minus c squared. It's there. 1/2 psi double prime over b minus c squared. And it so happens that basically this one And this one, if you put them back into psi double prime, they just get a factor 6 here, 6 times dt. Okay. So this has to be equal to 0. And here you see, okay, maybe this was slightly messy, you know, this description, you know, of what is ethos calculus for semi-martingales here. I just want to make sure, I mean, to explain that, you know, especially in the present, you know, configuration, it's just, you know, doing Taylor expansions and checking that, you know, up to second order and checking that things work out well. So there's nothing deep, no deep theory here behind the scene. Okay, so this has to be equal to 0. Now, there's one thing that I explained you at the beginning, which was that gamma, and therefore W, you know, they are given first, and then we choose B and C. Right? And so this basically has to be true for any set of B and C's. And it's quite clear here from the picture here and the definition of psi prime and psi double prime that if you want this guy to be 0 for any psi, I mean any choice of initial choice of B and C, you'd rather want basically that this quantity here is 0 and that this quantity is 0. Right? Because you can always choose, you know, two choices of initial B prime, C prime, such that this and this, you know, are not, you know, proportional the same way for both, and therefore, by just doing linear combination for the two choices of B, C, or B prime, C prime, what you end up with is that basically each of these two terms here have to be 0. Okay. So what we do here is we use our martingale xt, but actually we don't use just our martingale xt, we use two martingales. You know, one martingale xt for one given choice of points B prime, C prime, and another martingale m prime t or m tilde or m hat t corresponding to the choice of B hat and C hat, which are two other points on there. And in particular, using these two things, what you end up with is that this has to be 0 and this has to be 0. And so what does this mean? This means just that Vt is 0, so this means just that W is a continuous martingale, right? Because Mt plus Vt was the decomposition of Wt, you know, in a continuous martingale in a finite variation term. And Mt is 6 times t, which just means, you know, that m is a martingale running at speed 6 times t. Is a Brownian motion running at speed 6 times t, and you're done. So of course, you might say, well, you know, there's a big miracle going on, you know, how can it be, you know, that everything simplifies so well? I mean, you knew from the start that that was what you had to get in the end. Something like that. Because you knew from the start that if, okay, I assume if you believe, okay, this is what we just proved here, but if you believe that the scaling limit of the percolation interface is conformal invariant and has a nice scaling limit, right, then because it satisfies, you know, the discrete Markov exploration property, in the scaling limit this will still be true, so the driving function of the scaling limit should be a process with independent ID increments. It's continuous. There's no reason, you know, that it goes more to the right than to the left because of left-right symmetry of percolation. So it has to be a Brownian motion running at a certain speed, right? So if things, you know, if the world stands right, since we knew that you know, Cardy's formula was coming out, we knew Cardy's formula, then necessarily, you know, Cardy's formula should be a martingale for one of the, if you replace W by one of the Brownian motion running at a certain speed. Has to be like this. You know. So it's not a, you know, terrible coincidence, you know, that here what you end up is something that here everything simplifies by this times dmt minus 6 times dt. No, it's just that if mt is time the constant time dt, the well-chosen constant time dt, then this has to be 0. Okay, but here we go the other way around. You know, we start with Cardy's formula and just say that, knowing that the fact that Cardy's formula produces continuous martingale, that this is actually enough to say that Wt is a Brownian motion running at speed 6 times t. And this is a big difference. So, so if you look at the proof by Kamiya and Newman, what they do is they say, let us prove, directly, that the driving function of the scaling limit has to satisfy the continuous Markov property by just, brute force, not using this argument. And here, you get it for free because once you identify the continuous martingale, then you are done because you have a Brownian motion behind, and then you can, do this little trick saying that if there's a Brownian motion on the other side, generates the right xt is a martingale in infiltration, so Wt is a semi-martingale of the same filtration, and then you can go back and just play with Ito's formula back and forth, and you don't have to do anything. You end up with the fact that gamma t is generated by Brownian motion running at speed 6 times t, and therefore now we can say it satisfies the, this exploration property because it is a process. Wt happens to be a process with independent increments. But here you get it only at the end of the proof. So conclusion is that so I already said if gamma is the subsequential limit of so on, then gamma is a Loewner chain generated by Wt, which is Brownian motion running at speed 6 times t. And so now it's finished because we have said whatever subsequential limit of my tight sequence of probability measure we're looking at, the subsequential limit is the law of a Loewner chain generated by Brownian motion running at time 6 times t. So this law is unique. It's always the same. Right? So if you have a tight sequence, or tight family, there's just one subsequential limit. That means that the family converges as delta goes to 0 to this to this limit. Right? Conclusion. Gamma delta converges in law to SLE6 as delta goes to 0. So that's the end of this proof, where this convergence in law corresponding, remember, to this parameterization, modulo increasing, this metric, uniform distance with respect to uniform reparameterizations of time reparameterization of your curve. Now, what this tells you, remember, there was what I've described to you first was this equivalence that we had last time between Loewner chains generated by a continuous function W, right, and increasing family of compact sets that are parameterized by their capacity and that are growing locally. Okay, and I have never said, that when I take, W to be a Brownian motion, then this guy that you get K increasing family of compact sets defines actually a curve, gamma, or corresponds to the inside of a hull of something created by a random curve. What you get for free here, because of this proof, is gamma delta converges in law to the Loewner chain. It's not, here you have to be careful, right? What I said is gamma delta converges in law to a random curve delta, a random curve gamma, and if one defines KT the inside of the hull, right? A gamma t plus all the loops, you know, that are created inside gamma up to time t. Then this kt corresponds to the Loewner chain derived by what you get if you take wt to be Brownian motion running at time 6 times t. So, in other words, a byproduct of this result here is the fact that SLE6, so the following is true. I take a Brownian motion running at times 6 times t in the real line. I define the Loewner chain starting from this guy. This is an increasing set of compact hulls, which has a certain law. So you define a random family of increasing kts. And this family has the property that there exists a continuous curve gamma such that kt is equal to the hull of gamma up to time t. So in other words, you know, the type of pathologies that Christophe has been describing about that you don't always know that an increasing family of hulls, you know, maybe they winds like this, and in that case, the increasing family of compact set gamma t does not correspond to a continuous curve. This does almost surely never happen in the SLE6 picture. And this is a difficult result, you know, to prove that. That's a paper by Odette Schramm and Stefan Roeder, that SLEs in general are not, you know, correspond to actual real curves. When kappa is larger than 4, this is really not easy. So, but here you get it for free. Another thing you get for free, which is another difficult result about SLEs, which is going even further. If you imagine that SLEs correspond to simple curves, you know, going from A to B here in my domain, that the law of the curve from A to B, if I take this to be an SLE6, and I look at its time reverse, so now I look at the curve going from B to A. Right. Then what I just said is that the law of this curve is the scaling limit of the percolation interface, and therefore the percolation interface in one direction and the other direction in this discrete case are the same curve. And so if I take the limit when delta goes to 0, SLE from A to B, time reversed is an SLE from B to A. But that's if I time reverse the curve, not if I time reverse, you know, the hulls, then I'm in trouble. If I time reverse the curve, then from B to A and A to B, then I get the same guy. That's a difficult result in general. So that has been proved just, you know, very recently by Dapeng Zhang, the fact that SLEs in general are reversible. So that SLE, if I take in any other kappa, first of all, Schramm-Roeder said, I know that it's generated by a curve, and Zhang then said, yeah, and also this curve has this law of reversibility. So in the SLE framework, it's very non-natural, you know, to look at things backwards in a way, because they are created, you know, the hulls, you know, that are created in this way appear, you know, are very non-reversible in some sense. But if you know it's a scaling limit of a discrete model, then you have the reversibility for free. That's just one example of it. So this result, you know, already proves things that are highly non-trivial for in the Loewner framework. Okay, so I guess that's a good time to make the break now, and in the rest of the lectures, we'll try to see, okay, how can we use this result, you know, to prove something concrete about percolation. So remember, so I think you have seen by now sort of all the different steps of this proof, and you recognize that it's, on the one hand, you know, it's technically quite long. It took me several lectures. On the other hand, you know, everything is natural. You know, it's not like, you know, you need to invent. Once you know what you are aiming at, it's quite clear what the different steps are going to be and how you're going to solve them. And each time you don't have to find, you know, extraterrestrial arguments at each step. It's just, you know, things are natural. Okay. So maybe just for those who went to my Ising model afternoon sessions, you see this type of arguments is likely to go through. It actually goes through in other cases. So if you have conformal invariance of one observable, like what is going to be replace Cardy's formula, it's just the explicit function of explicit function psi that you get here, roughly speaking. So once you have you know the different function psi here, then this type of argument will go through the same way. Of course, then you have the tightness issue to take care of to start with, which depends on the ad hoc problem that you're looking at. But other than that, this type, as soon as you have convergence of one observable, then roughly speaking, that's enough to get the convergence of the SLE itself once you have tightness. Yes?
Would you mind repeating again this comment you made about the proof of Camille-Newman for that result you said?
No, I just said, you see here, we have, okay, here what we do is the following step. We say, tightness says we have subsequential images that are curves. We know there are Loewner chains. And once we have this, you see the way we get that we have a Brownian motion here is just saying it is a semi-martingale. So we don't know, and at the very end, we recognize that this semi-martingale has a 0 thing here, and that this guy is constant and equal to 6 here. So it's a Brownian motion running at speed 6 times t. And therefore, you can, and then at the very end, you say, well, actually, look, this is Brownian motion running times 6 times t, so it has this exploration property, which is that the scaling limit, any subsequential scaling limit gamma, will have the property that will have this property, which is that I know this gamma up to here, I map it back to my original domain, I get this the curve gamma itself. Here's just a problem. If you want to prove this property directly, here's the type of problem you run into. Take delta n go to 0. Right? You take one subsequential limit. Take the curve up to time t here. Right? Map it back onto the original domain. Right? So map this remaining domain here on this original thing. Is it the same as the law of the curve we started with? Well, we don't know exactly because, the delta n's are distorted now. Maybe here, it's not exactly the same delta n we started with because we take one particular subsequential limit, right? And so the fact, that you cannot just interchange, the fact that you take a subsequential limit and then it's invariant on a conformal transformation. This you can do only once you know that there's just one limit. So that's the type of problem so their strategy was say, well, let's prove, that any subsequent, roughly speaking, I'm just simplifying things, but let's prove that any subsequential limit, has satisfied the conformal Markov property, and then, we say no, it's Brownian motion, and we identify the kappa by the value. But here you see that there's to prove directly, to work directly with the conformal Markov property here, this is a very problematic thing. And here, in a way, you circumvent it by of course, in the end, you prove the same thing, so I'm not saying there's a huge difference. But, this is sort of makes life much simpler there. Okay, it's